Let us study potential due to a point charge. Consider a point charge Q at the origin. We are going to determine the potential at any point P with position vector r from the origin. For that, we must calculate the work done in bringing a unit positive charge from infinity to the point P. For Q greater than 0, the work done against the repulsive force on the test charge is positive. At one intermediate point P prime on the path, the electrostatic force on a unit positive charge is Q into 1 divided by 4 pi epsilon naught r prime whole square into r cap, where r prime is the unit vector along OP prime. Suppose the charge is moved further from P prime by a distance delta r prime, then the work done against the force from r prime to r prime plus delta r prime is delta w is equal to q by 4 pi epsilon naught r prime whole square into delta r prime. If delta r prime is very small, then delta r prime tends to dr prime. Similarly, delta w prime tends to dw prime. This implies dw prime equals q divided by 4 pi epsilon naught r prime whole square dr prime. Total work done W by an external force in bringing a charge from infinity to P is obtained by integrating from infinity to R. W equals infinity to R minus dw, which implies W equals integral infinity to R minus q by 4 pi epsilon naught r prime square dr prime. On solving the equation, we get W is equal to q by 4 pi epsilon naught r. By definition, this work done is stored as potential energy at point P due to charge Q. Thus, VR equals q by 4 pi epsilon naught r. This equation is true for any sign of the charge Q. For Q less than 0, the potential is also negative. This means that the work done by the external force per unit positive test charge in bringing it from infinity to the point is negative. That is, VR equals minus Q divided by 4 pi epsilon naught r. One more thing to be noticed is that the potential V is inversely proportional to distance, while the magnitude of electric field E is inversely proportional to the square of the distance between the two charges.